Hello everyone, welcome to my YouTube channel TechSpot. This is me Harishgoupale. So basically in this video we are going to discuss about the operators. Basically what are the operators are available in the Verilog for the design implementation of various types of circuits that we are going to discuss in this video. But before going to start the video, I request you, if you are new to this YouTube channel, then please subscribe to my YouTube channel. Also press bell icon for the notification. Okay, so let's get start with the Verilog operators. So basically in Verilog we are having different types of operators such as arithmetic operators, logical operators, equality and inequality operators. Then bitwise operators also we are having, and then relational operators, reduction operators, and cheaper operators. Okay. So first we'll discuss about what are the arithmetic operators are available in the Verilog. So the first is addition, which will perform addition of two binary operands. Then subtraction is there, which will also perform subtraction of two binary operands. Then multiplication operators, which we have, that is also going to perform the multiplication of two binary operands. Then we are having division operator, which is going to perform division of two binary operands, but division operator will return the quotient. Okay. And for the remainder, we are having modulus operator, which will perform modulus of two binary operands and will return the remainder. Now we'll jump to implement these all the arithmetic operators on the Verilog design. So here on my screen you can see I have written a Verilog code for the design implementation of all the arithmetic operators. So let's understand each line of code one by one. So here I have provided time scale 1 nanosecond divided by 1 picosecond. Nanosecond, 1 nanosecond is the time unit and 1 second is the 1 ps is the time precision. Then my module name is arithmetic operators design, and I am having two inputs A in and B in of having which is size is 5 bits. The first output is add out. So add out size is 6 bit. Why 6 bit? Let's understand by this example. So if for example, if suppose you want to perform addition of 2 bits, so the highest value of 2 bits will be 3. So operand 1 value is 3 and operand 2 value is 3. And if we add this 3 plus 3, the addition will be 6. And we cannot represent 6 with 2 bits. We need at least 3 bits to represent the 6. So that is the reason we need one additional bit with existing bits. Okay, so if you want to perform 5 bit of additions, we need 6 bit results to store the results of the additions. Okay, now the second output is sub out, which is having 5 bit only, 5 bit result out. Then multiplication out, we need 10 bits. I have taken 10 bits. Why 10 bits? Uh, Understand here also, here only, 2-bit operands, the highest value is 3. So if we multiply 3 multiplied by 3, output is 9. Again, 9 can't be represented by 2 bits, it needs 4 bits. That means if you want to perform the multiplication of two operands of any size, so we to store the result of that multiplication, we need a storage of double the size of the operands. That means if the operand is 5 bit, we need a result of 10 bits. Okay, that is the reason I have taken 9 down to 0, multiplication out. Then division out and modulus out, the size is 5 bit only. Okay, and then here I am using always at the rate star procedure block. Basically this is combinational. Okay, then inside that I am assigning a in plus b in to the add out, a in minus b in to the sub out, a in multiplication of b in to the multiplication out, a in divided by b in to the division out, and a in modulus by b in to the modulus out. As I already told you, a division operator will return the quotient and modulus operator will return the remainder. Okay, and the important thing is all the operators plus, minus, multiplication, division, modulus are synthesizable. Okay, now to verify this, I have written simple test bench code in the system Verilog. Okay, So here you can see, let's understand this code, this line of code one by one. Here also modulus name TB arithmetic operators. Then all the variables I have taken, A, B, subtraction, addition, multiplication, division, modulus, A and B are the inputs, remaining are the outputs. Then the instantiation, arithmetic operators design, and instant design is the instance name. Inside that, A in is the name of a design file. This A in, B in, and this variable A and B are belongs to this TB5. Okay, this is how we have to do the instantiation. Then inside the initial begin, I have initialized the value of A and B. Okay, so first we'll see the schematic. What is the schematic this will give? Here on my screen you can see the schematic. A in, B in, this addition operator, division operator, modulus operator, multiplication operator, and subtraction operator. Now we'll click on this run simulation. Okay, this will give the schematic waveform. Okay, so here you can see the value of A is equal to 10, B is equal to 5u. So subtraction is 5u, A minus B, 10 minus 5u, 5u. Addition is 15, multiplication 10 multiply 5u, 50, and division 2, 2 because 5u, 5u 2s are 10. So quotient is 2 and the remainder is 0. Modulus will be given the remainder. Okay. Now in second, after 10 nanosecond delay, A value is 30, B value is 10. So subtraction is 20, addition is 40, uh, addition is 40, and multiplication is 300, is 3, again modulus is 0. Okay, so this is about the arithmetic operator. Let's see what are the logical operators are available in the Verilog. So the first operator is logical AND, basically which perform logical AND between two operands. Then logical OR we are having, which will perform a logical OR on two binary operands and will give a result in the form of true or false. Okay, then negation will be performed on the single bit operands. Okay, then we are having equality and inequality operators in the Verilog. So the first is case equality, which will check whether both operands are equal or not. And in case inequality operator, it will check that both operands should not be equal to. Okay. Similarly, we are having relational operators in the Verilog, that is greater than means it will compare operand values whether operand 1 is greater than operand 2 or not. Similarly, with greater than equal to, it will check whether operand 1 value is greater than or equal to with operand 2 value or not. Okay, then we are having less than, which will check whether operand 1 value is less than operand 2 value or not, and less than equal to will check operand 1 value is less than or equal to with operand 2 value or not. Okay, now we'll jump to implement all these operators in the Verilog design. Okay, here on my screen you can see I have already written code for the design implementation of logical operators, equality and inequality operators, and relational operators. So let's understand the each line of code one by one. Okay, so the module name is logical and relational operators. Input I am having 4-bit inputs A in and B in. The first output is logical AND of a size 4-bit. Second output is logical OR of size 4-bit. Third output is negation of size 4-bit. Then I am having a single output equality, single output inequality. Then the output greater than is 4-bit of output. Then greater than equal to is also 4-bit out of 4-bit of output. Less than is 4-bit of output. Less than equal to is also 4-bit of output. Then I am using here a combinational block, that is albeit at the rate star. Star basically automatically implement sensitivity list. Okay, we don't need to give the signals inside the brackets. Okay. Now here you can see I have assigned A in logical AND with B in to the output logical AND, and A in logical OR with B in to the logical OR output. And negation of A in will be stored the result in the negation variable. Okay. Now now here you can see the condition. if A in is equal to B in. This is for equality check. If both operands are equal, then equality will be high, and in that time inequality will be 0, greater than will be 0, less than will be 0, greater than equal to will be 1. Because of this equal to, and we are here, we are also checking equality, so that is the reason I have assigned value 1 to the greater than equal to variable, and less than equal to output will be assigned to as a 1. Okay. And in else if condition I am checking whether operand A is greater than operand B in. If it is, then greater than value will be store the value of A in. Greater than, I am assigning the value 0 to the greater than equal to output. Then equality, obviously both operands are not equal, so I have assigned 0 to the output equality and 1 to the inequality. Okay. And obviously if A is greater, then B is less than, so I have assigned value B in to the less than output, and less than equal to will be 0. Then in else if condition, now I am checking whether A in is greater than is equal to B in. So I have assigned A in to the greater than value. Okay. And greater than equal to also, I have assigned A in to the greater than equal to output. And if A is greater than equal to B in, then obviously B in will be less than. So I have assigned B in to the less than, and B in to the less than equal to. In this case, equality will be 1 because of the greater than equal to, and inequality will be 0. In else if condition, I am checking whether A in is less than B in. Okay. So if it is if it is like that, then less than, then assign A in to the output less than, and at that time I have assigned 0 to the less than equal to. Okay, because it is not equal to, it is less than only, so that is the reason I have assigned 0 to the less than equal to. Okay. And 0 to the equality and 1 to the inequality, because both operands are not equal. At that time, if A in is less than, then obviously B in will be greater than. So B in I have assigned to the greater than output, and greater than equal, and 0 I have assigned to the greater than equal to. Okay. In else if condition, I am checking whether A in is greater than or equal to B in. If it is like that, then I have assigned A in to the output less than, also same A in out to the output less than equal to also. At that time equality will be high because of this less than equal to value, a less than equal to operand. And obviously if A in is less than, then B in will be greater than, so I have assigned B in to the greater than, and B in to the greater than equal to also. And in else condition, I am checking. In else condition, it will check whether A in is not is equal to B in. So I have assigned 0 to the equality, 1 to the inequality. Obviously, greater than 1 to the greater than, 1 to the less than, and 0 to the greater than equal to output, and 0 to the less than equal to output. See, I have written this code just to implement the operands. Okay. I have written this code as I thought. You can also write a code as per your way to understand the working functionality of each operators. Okay. Then for the verification of this design code, I have simply write a test bench code also. Let's understand the each line of code. The module name is TB logic operators. Okay. And the same variables, I have taken the number of variables which is used for the design implementation of all the operators. Okay. There also A, B, and out, or out, negation, equality, inequality, greater than equal to, all the variables are here. Now this is the instantiation. Logical and relational operator is the name of a design module, and instance logical is the instance name. And then this A in belongs to the design variable, and this A belongs to the TB variable. Okay, this is how we have to do the instantiation. And in the initial begin, I have assigned some value of A and B. Okay, now we'll discard this. First, we'll check the schematic, and then we'll run the simulation. So here you can see in schematic. Hmm. The schematic is a little bit complex. Okay, so we'll jump to run simulation only. And here we'll click on this. because I already run this. And we'll see the waveform. In the waveform, you will see the outputs. Okay. So first we click on this, then bigger. Again. And we'll check all the values in the form of unsigned decimal. Okay, so here you can see value A is 10, value B is 10. Now and out is 1. Why 1? Because see, operand A is also having one value, operand B is also having one value, and the logical AND says that if any operand is 1 1, output will be 1. Okay, so that is the reason here also and out is 1. Similarly, or out, if in or out what 1 0 1 1 1 or 0 1, in all three conditions it will give the output 1 only. Only it will give the 0 in which condition, when the combination of 0 0 is there. Okay, now negation of A, obviously it will give the 0, because the value of A is more than 1 right now. Okay, equality, you can see both are not equal, so that is the reason equality is 0 and inequality is high. Okay, because both operands are not equal, unequal. Okay, then 10 is greater than, so greater than value is 10, greater than equal to 0, because I in design I have assigned 0 value to the greater than equal to. Okay, less than, here 5 is less than, so 5 is assigned to the less than output, and less than equal to again 0. Similarly, here also the operand A value is 15, operand B value is 12. So like operand A and operand B is more than 1. So output is high, or output is also high. Negation is 0, and inequality, yes, both are not equal. So that is the reason equality is low and inequality is high. Then greater than 15 is greater than, so 15 is assigned to the greater than. Greater than equal to 0 I have assigned to the greater than equal to in the design part. That is the reason in output we are getting 0. 12 is less than, that is assigned to the less than output, and again here is 0. Now here you can see I have given similar value. Operand A is 0, operand B is 0. So here you can see and out is 0. That means it says whether operands 1 and operands 2 are 0 0. So yes, and out is 0. R out is 0. Negation is 1. Operand A is 0, so negation will be 1. Equality, yes, both are equals. So equality is high, inequality is low. And then greater than, this time greater than is 0. Greater than equal to, yes, both operands are equal to. That is the reason greater than equal to I have assigned 1. Less than 0 and less than equal to 1. Yes. So in this way, I have implemented all the logical operators, equality and inequality operators, and relational operators in the design file, and this is how I have understand. We'll see what are the bitwise operators we are having available in the Verilog. So the first is bitwise and, which will perform bitwise and on two binary operands, but it will perform the operation bit by bit. Okay. Similarly with bitwise or, that is also, which will also perform the operation on two binary operands, and similarly with bitwise XOR also. Also we are having shift operators in the Verilog, so that is shift left, which will perform left shift on two operands. That means it will, for example, if operand 1 is value 2 and operand 2 is value 1, so the operand 1 value will be shifted by the 1, the because operand 2 value is 1. Okay, whether it will be right or left, that will be depends on the operator, uh, shift left and shift right. Okay, now we'll jump to implement these operators in the Verilog. Here you can see on my screen, I have already written a Verilog code for the design implementation of bitwise operators and shift operators. So let's understand this code offline one by one. So the module name is bitwise and shift operators. Input is similarly like previously we have implemented code 4-bit of input A in and B in, and the first output is bitwise and of size 4-bit, bitwise or of size 5-bit, sorry 5-bit, bitwise XOR of size 5-bit, left shift of 5-bit and right shift of 5-bit. And I have used the procedure block always at the rate star begin in, assigning A in bitwise AND with B in to the output bitwise AND, A in bitwise OR with B in to the output bitwise OR, A in XOR with B in to the output bitwise XOR, and A in left shift with B in to the output left shift, similarly to the output right shift. Okay, and to verify this design code, I have write simple TB code. The TB code, let's understand this TB code also. The module name is TB for bitwise and shift operators. Then the variables A, B, bitwise AND, bitwise OR, bitwise XOR, shift left, shift right. Each of variable having size 5 bits. Okay. Then this is the instantiation bitwise and shift operators. Instance design is the instance name. Okay, and in the initial begin I have assigned some values in the form of bits only. Okay, now we'll click on the schematic or to see the schematic of this. So here you can see the schematic bitwise and bitwise or bitwise XOR, left shift and right shift operators. Okay, these are the gates, these are the operators. Okay, this is the circuits. And now we'll click on this run simulation. So I have already run this. We'll see the waveform. Here you can see the waveform. The value of A is here uh, 0 1 0 1 0, and value of B, operand B having value 0 0 0 1 1. So bitwise AND, as we know, the truth table of AND, in AND gate, if there is if both operands, if both bits are 1 1, then only output is 1, otherwise output is 0. So you can see this 0 1 is 0, 1 1 is 1, remaining 0 0 0 1 0 0 0 0 0. Okay, being bitwise OR, we know that if there will be 0 0, if value of both operand is 0 0, then only output is 0, otherwise output will be 1. So you can see that 0 1 1 1 1 1 0 0 0 1 0 1 0 0 0. Okay, in bitwise XOR we know that if both operands are inverse, then output is 1, otherwise output is low. So here you can see 0 1 is 1, 1 1 0 0 0 0 1 0 1 0 0 0. Okay, shift left, shift left, here you can see the operand A is having value 10 and operand B is having value 3. So so the operand 1 value will be shifted by 3. Okay, so if you see we have to shift this 0 1 0 1 0. So once so if we, after shifting 3 times, this 1 will come to this. So you can see the output 1. This one means 1 2 4 8 16. Okay, so here we got the output 16. Okay, means operand A value shifted by 3 because B, operand B value is 3. Okay, similarly in shift right, it has shifted the operand A to the right. So this one became, one come here. You can see the output. Okay, similarly here also. Okay, so this is how we can implement all the operators like bitwise and shift operators. As I already told you, you can implement in your own way also to understand the functionality of the all the operators. Okay, let's see what are the reduction operators we are having in the Verilog. So the first is reduction AND, which will perform bitwise AND operation on a single operand. Similar like reduction AND, we are having reduction NAND, reduction OR, reduction NOR, reduction XOR, and reduction XNOR. So all the operators will perform operation on a single operand. Okay. Let's see the design implementation of reduction operators in the Verilog. So as you can see on my screen, I have already written a code for the design implementation of the reduction operators. Okay, so let's understand this code. Okay, so the module name is reduction operator design, and I am having only single operand. And then output reduction AND of 5 bit, reduction OR of 5 bit, reduction XOR of 5 bit, reduction AND similar like reduction OR and reduction XOR. And then I have used always @ star procedural combinational procedural block, that is combinational block, and I have assigned reduction AND of in to the output reduction AND, reduction OR of in to the output reduction OR, XOR of in to the output reduction XOR, NAND of in to the output reduction NAND, NOR of in to the output reduction NOR, and XNOR of in to the output reduction XNOR. Okay. To verify this code, I have written simple system Verilog code, that is the module TB for reduction operator, and then the variables A of 5 bit, all the outputs of 5 bit, reduction AND, reduction OR, reduction XOR, NAND, NOR, XNOR. Then this is the instantiation, and inside the initial beacon I have assigned the value of A to see the output. So I'll click on the schematic to see the circuit, what circuit it has created. As you can see, A is the output, and the circuit of AND, NAND, okay, OR, then that is NOR, OR, and that is XNOR and XOR. Okay, and we'll click on run simulation to see the waveform. As I already run the simulation, I'll just click on this so that it will give me the updated waveform. Okay, and we'll check the values, how it is performing the operation by using reduction operators. Okay, I click on this. We have already output in the form of binary. We'll check the so here you can see the input A is 10101. Now reduction AND. Now how it is performing and our reduction AND. See, so it is performing 1 and 0. As we know that the truth table of AND gate, if both operands are high, then only output is high. Otherwise output is low. So 1 and 0, 0. 0 and 1, 0. 0, 0, 0. 0 and 1, 0. Output is 0. Here also 0 and 1, output will be 0. Then that 0 and 0, output will be 0. 0 and 1, output will be 0. Again 0 and 0, output will be 0. So in both values, the output of reduction and is 0. Reduction or 1. So how 1? See, 1 and 0, we know that 1. We know the truth table of OR gate. If both operands are 0 0, then only output will be 0, otherwise output will be 1. So 1 0, output will be 1. 1 1 1, 1 0 1, 0 1 1. Output I got 1. Here also 0 1 1, 1 0 1, 1 1 1, 1 0 1. Output is 1. Okay. In the in reduction XOR, in XOR, as we know that if both operands are inverse, output is high, otherwise output is low. So 1 0 1, 1 1 0, 0 0 0, 0 1 1. Output is 1. Okay. In this case 0 1 1. Now 1 0 1, 1 1 0, 0 0 0. Here you can see the output 0. In now also I got the output as 1, and the reduction NOR 0. Here you can see reduction R is 1. The out as we know that NOR is the inverse of OR. So here we got the 0, and the reduction of XNOR. We know that XNOR is the inverse of XOR. So here it was 0. Here is it. Here the output of XOR was 1. Here we got output of XOR is 0. Here the output of XOR was 0. We got here 1. So this is how I have implemented the reduction operators in the Verilog code. So here we have almost covered all the types of operators such as arithmetic, bitwise, logical, equality, inequality, relational, reduction. And the main thing is all the operators are synthesizable. You can easily implemented. And here I will